Hello and welcome back to Anton Math. Now in the last video we talked about inverses and zero divisors. And in this video I'm going to go over a useful tool to know whether or not a number has an inverse. And then we're going to do an example with some big numbers to see how we can find the inverse if we're dealing with a large number and a large modulus. It's not always so easy to see what that inverse is going to be. But we have some methods based around the Euclidean algorithm that we learned in the last section that are going to help us find that inverse very quickly. Alright, so let's take a look. So first a theorem that's going to help us out. Suppose an integer, or suppose a is an integer that is not congruent to 0 mod n. Now n is my modulus and a is my integer not congruent to 0. If the GCD of a and n is 1, so in other words if they're relatively prime, if my number is relatively prime to the modulus, then it has an inverse mod n. If it is not relatively prime, or if the GCD of a and is not 1, then a is a zero divisor mod n. Now I haven't done a proof for a while, so let's go ahead and do a little proof for this. Proof skis. I'll prove part I first. So I'm proving that if the GCD of a and n equals 1, then a has an inverse mod n. And this is going to be from our results with the linear combinations of GCDs with our Euclidean algorithm. Right? I know that there exists a x and a y in the integers such that the GCD of a and n is equal to ax plus ny. Right? This is what we did in the previous section. We actually found these linear combinations, but we always know that they exist. We can write the GCD as a linear combination by using the reverse Euclidean algorithm. Well, since my GCD is 1, then 1 equals GCD of an. But now modulo n, ny is congruent to 0, right? Because n divides n, so ny is congruent to 0. So the GCD of an is congruent to ax mod n. Well, so I'm getting that a times x is congruent to 1 mod n, right? This reads both directions. So this implies that a inverse is congruent to x mod n. We can think of this in two different ways. Either I'm looking at 1 congruent to ax, and I multiply both sides by a inverse. A inverse becomes 1, so I have x on the right, and 1 times a inverse is a inverse on the left. Or I can just know, well, if a times x is congruent to 1, that means that x is a inverse, because that's how we defined the inverse of a. So we're done with part 1. That completes the proof. If the GCD is 1, a has an inverse. And we can find it, this is key, we can find it by using the linear combination of the GCD. We can find the inverse. That's how we're going to find it later. But let's finish this proof out. Part 2, if the GCD is not 1, then a is a zero divisor. So this one's a little bit more tricky, but not too bad. Suppose that the GCD is greater than 1. Right? That's what it means if it's not 1, because we know it's going to be an integer, a positive integer. So let's suppose that the GCD equals d, and that d is strictly greater than 1. Well, d is my GCD, so d divides a, d divides n. So this implies, or not implies, I could say so, a equals dx and n equals dy for some integers x and y. Right? That's what it means for d to be a divisor. If d is a divisor, and I know x and y are positive, because when we talk about GCD, we really mean greatest common factor. So d is positive, a and n are positive, so that means that x and y are positive. So there exists some x so that a equals dx, and some y so that n equals dy. This is what it means for d to be a GCD. Well, as a result of this, we know that d is greater than 1, and that is going to imply, looking at this equation right here, that y is less than n. Right? If n equals d times y, d is greater than 1, then obviously y doesn't equal n or anything bigger than n. It must be less than n. We also know that y is not 0 because we're not doing arithmetic modulo 0. We're doing arithmetic modulo n. So d greater than 1 implies that y is less than n. So in particular, y is not congruent to 0 mod n, right? Y is not congruent to 0 mod n. But let's look at this. If I take a and multiply it by y, I can substitute in, that's going to be the same thing, looking over here at my a equals dx, that's the same thing as dx y. Now, dxy, I can look at this dy from this part over here, dy equals n, so this is just nx, and of course nx is congruent to 0 mod n. Now what have I shown? Well, I've shown that there's some number y that is not 0 mod n, that when I multiply it to my a, which is also not 0 mod n, then I get 0 mod n. So in particular, a is a zero divisor. Now, I just realized I haven't really shown you something. I haven't shown you that a number cannot have an inverse and be a zero divisor. So let me show you that real quick. It's a pretty simple argument. Let's say A has an inverse and is a zero divisor. Modulo n. Now I've assumed something that I know is wrong, so of course I'm going to try to do a proof by contradiction here, right? I've assumed something wrong, I want to find a contradiction so that what I've assumed, the opposite must be true. I remember this from our kind of proof section. I'm going to do a proof by contradiction here. So if A has an inverse and is a zero divisor, that means that A inverse is congruent to 1 mod n. Now let's just say that the other zero divisor complementing A is y. Let's just say that AY is congruent to 0 mod n, where y is not congruent to 0 mod n. Right? This is what we call a zero divisor, is if both of these values are non-zero and their product is 0. So if A has an inverse and a zero divisor, well then I can multiply y to this equation and I get A inverse is congruent to y mod n. But AY is 0, so this gives me that 0 is congruent to y mod n. And this of course is a contradiction, because from over here I have that y is not congruent to 0 mod n, and over here I have that y is congruent to 0 mod n. This is my q and not q, which we know is impossible. So of course A either has an inverse or it is a zero divisor. It cannot be both. So now let's do an example with some big numbers like I promised on using this result to try to find these large inverses. So example, which of the following are zero divisors modulo 224? If the number is not a zero divisor, find its inverse. Now I'm not going to go through the work of finding the GCDs of all these numbers in 224. This will be a good exercise for you to do on your own. Make sure you're getting the same thing that I get here. But looking at our solution, I have that GCD of 16 and 224 actually equals 16. The GCD of 53 and 224 is equal to 1. The GCD of 63 and 224 is equal to 7. The GCD of 84 and 224 is equal to 28. And the GCD of 97 and 224 is equal to 1. So, from our theorem, 16, 63, and 84 are zero divisors. Right? Recall our theorem we just had. I know I kind of went on a little tangent there. So just to remind us, if the GCD of A and the modulus is not 1, then A is a zero divisor. So for all of those numbers I just listed, the GCD is not 1, right? We have 16, 28, and 7 for those three numbers. So those three numbers are zero divisors. So that means that 53 and 97 have inverses. So let's find those inverses. Now first, I'm going to find, I'm going to find the inverse of 53 first. And I'm going to use the Euclidean algorithm. The Euclidean algorithm. Right, this is what we used to find GCD before, but now we can use the same process to find inverses. But I'm going to need to use the extended Euclidean algorithm, where I do the reverse algorithm to find that linear combination. And we'll see why here in a second. We've already kind of used it in the proof. But first, 224 is equal to 4 times 53 plus 12. 53 is equal to 4 times 12 plus 5. 12 is equal to 2 times 5 plus 2. 5 is equal to 2 times 2 plus 1, and of course 2 is equal to 2 times 1. This is actually going to be a little bit longer than we're used to, isn't it? But we knew the GCD was 1, so it does take us a little bit to get there. So I'll go through this reverse algorithm a little quickly. 1 equals 5 minus 2 times 2. Now I can substitute in for 2. This is going to be 5 minus 2. Subbing in for 2 from here, I get 12 minus 2 times 5. Simplifying this and combine these 5s, I have a plus 4, 5 plus 5. So that's 5 times 5 minus 2 times 12. Now I can sub in for my 5 from right here. 5 is equal to 53 minus 4 times 12. And I still have this minus 2 times 12. And just a quick note, sometimes you'll see people substituting in for 5 and 12 at the same time, and that's absolutely fine. I like doing it one at a time and then simplifying. The reason is if I substitute for 5 and 12 here, I'm still going to get another 12 right here, so I'm going to have to substitute in for 12 again. I'd rather just do it all at once. So this gives me 5 times 53. And looking at my 12s, I have negative 20 minus 2. So this is minus 22 times 12. Now my last substitution for 12, 5 times 53 minus 22, and 12 is equal to 224 minus 4 times 53. And simplifying out a bit, let's look at my 53s first. I have negative 22 times negative 4, so that's 88 plus 5. I'm going to get 93 times 53. I'm going to write this as plus negative 22 times 224. Now this is my linear combination for my GCD, right? But as a result from this linear combination, if 1 equals 93 times 53 plus negative 22 times 224, well, this part right here in particular is congruent to 0 mod 224. Right? And this is a shorthand for mod 224. If there's no risk of confusing it for multiplication, that's what this means. But this side is congruent to 0, right? So a result from this line right here is if I do a congruence to both sides of this, mod 224, I get that 1 is congruent to 93 times 53 mod 224. So in particular, that implies that 53 inverse equals 93. Now how would we have found this otherwise? Well, I could have kept adding 224 to 53 until I got 1. Or no, sorry, not 224. I could have kept adding 53 to itself until I got something that was congruent to 1 mod 224. And I would have had to do that 93 times to find this inverse using that method. Or I could have just gone through and multiplied by all of the residues mod 224 until I found an inverse. But really we see that this Euclidean algorithm gives us a way to calculate these inverses, and while it's not extremely short all the time, we know how long it's going to take us. We know it's not going to take us an hour and a half of trial and error. It's going to take us maybe 5 minutes of doing this reverse arithmetic. Now I still need to find 97 inverse, but now I'm going to use the matrix method. Remember that matrix method that gave us the linear combination already? But I'm going to adjust it a little bit differently. So so for finding 97 inverse, well, I'm going to look at this matrix here. It's like the matrix method we had before for the Euclidean algorithm, 97, 224. And remember, I have a 1, 0, 1, 0. Remember this? So it just means 97 equals x, or a, 24 equals b. So here I'm going to do my division, my Euclidean algorithm, and on this side it's going to create my linear combination. But remember before, when we just did 53, I didn't need this part here of my linear combination. This part of my linear combination is congruent to 0, and it's always going to be. And I don't need to really worry about it. So all that we really have to do when doing this matrix method, we can adjust this a little bit. I'm going to cut off this last column, and I'm only going to look at this 2 by 2 matrix, which of course is much easier to solve. Now in the end, I'm still going to have a hidden something over here. Once we get down to 1 in this left column, I'm going to have a third right column over here. I just don't care about it. It's not going to give me any information about the inverse, so to speed up my calculation, I'm just going to look at this 2 by 2 matrix. Now if that's not a good enough justification for you, you could also think of this matrix as the matrix of 97x congruent to 1 mod 224 and 224x congruent to 0 mod 224. If you think of the matrix as this way, well, this is obviously just a 2 by 2 matrix, right? We have our solutions on the right, and it's equivalent to what I'm trying to do with the adjusted Euclidean algorithm matrix. So let's go ahead and solve this out. Now normally we're just going to operate on the left-hand side to find the GCD, but now we know the GCD is 1. So we're going to go until we get down to 1 on the left-hand side, and then whatever's to the right of that 1 is going to be 97 inverse. So we'll make that connection there. But okay, so first thing I'm going to do is I'm going to do this 97. I'm going to multiply this by -2 and add it over here. 97 times -2 is -194. So that's going to give me a 30 on the bottom. I still have 97 and 1 on the top, and I'm going to have a -2. Okay, so now I'm going to multiply this 30 by -3 and add it up here. So that's going to give me 7, 6 on my top row, right? Or no, sorry, 7, 7. I have 97 minus 90 gives me 7. -2 times -3 is 6, plus 1 is 7. And then I have down here 30, -2. Now here's a temptation. When we did elementary row operations before, I could always divide by any commonality, right? So here, to reduce this matrix, I really could divide this top row by 7 and get 1, 1. Well, that would be okay in a sense for solving the matrix. But if we really want this matrix to be an emulation of our Euclidean algorithm, that's not what I want to do here. So refrain. Right? There are ways to do that, but I don't want to go into depth in that way. Better to just keep this process very clear-cut and similar to our Euclidean algorithm. So I'm going to multiply this top row by -4, add it to this bottom row. I'm still going to have 7, 7. Down here now I'm going to have 2, right? -4 times 7 is -28, so that gives me 2. And -4 times 7 is -28 minus 2 gives me a -30. And now final step, I'm going to multiply this 2 by -3 and add it to the top row. That's going to give me a 1. That's the one we're looking for. I still have 2 -30 on the bottom, although that's not so important anymore. -3 times -30 is 90. 90 plus 7 is 97. And now this top row, what does this top row say? This top row says x is congruent to 97 mod 224 from this system I have right here. Right? If we compare it to our Euclidean algorithm, this says 1 equals 97 times 97 plus something else times 224. But equivalently, looking at this system we created for the 2x2, if x is congruent to 97 and 97 times x is congruent to 1, then that implies that 97 inverse equals 97. And we're done. Now, it's just a coincidence that these numbers were the same. Most of the time, the inverses aren't the same. But you can go back and do this matrix method with what we did over here with 53, and you'll get the exact same solution that we got, that 53 inverse equals 93, and that'll be good practice. All right, that's it for modular arithmetic. I hope you all enjoyed this video, and this is the end of this course, for at least for the current semester, although I should be adding some material later. I hope it was helpful, and I'll see you all in class or later.